Everyone. My name is Sujith and today I'll be presenting my project titled Modeling and Control of a Wind Farm for Coupled Hydrogen Production in the Argentia Renewable Energy Project. This work focuses on integrating wind energy with hydrogen production, specifically in the context of a standalone renewable system developed for Argentia region in Newfoundland and Labrador. The project has been conducted under the guidance of Dr. Mohsin Jamil, and I am grateful for his support throughout his research. This study is part of the broader initiative at Memorial University of Newfoundland to explore green hydrogen as a viable, sustainable energy solution for Canada and beyond. Here is a quick overview of the topics I'll be covering in this presentation. I'll start with the introduction, where I will outline the background, motivation, and goals of the project. Then I will move into the literature review, which highlights key studies and current trends in wind hydrogen system and renewable integration. Next is the steady space modeling section, where I describe how the basic operating points of the system components were determined. After that, I will go to the system dynamic modeling, where I'll be presenting time domain simulations and control strategies, including the wind turbine, electrolyzer modeling, and control and protection schemes. This will be followed by the results, where I will show key outputs such as hydrogen production efficiency, voltage regulation, and power performance. Finally, I'll wrap up with the conclusion summarizing the findings and possible future improvements. Today, we are diving into dynamic landscape of renewable energy and its pivotal role in shaping our future. Specifically, we will explore how wind power and hydrogen production are driving the global energy transition. This project, we will focus on the transformative wind power, uh, where wind energies evolved from a niche technology to a powerhouse in the global energy mix. Modern wind turbines now boast capacities of 6 to 8 megawatt, directly feeding power grids and revolutionizing their operation with advanced power electronics. Hydrogen from renewables. Beyond electricity generation, renewables sources like wind offer vast potential of hydrogen production. This clean burning fuel presents a promising pathway towards a zero carbon future. Strategic advantage of offshore wind. The Department of Energy highlights offshore wind energy's particular advantage for hydrogen production. By generating hydrogen near the source of wind power, alleviate strain on overloaded transmission systems, making this approach even more attractive. Delve deep into the literature surrounding the intersection of wind power and hydrogen production, shedding light on key insights driving our project forward. In Canada, approximately 292 communities lack access to the national grid, predominantly relying on fossil fuels like diesel generators. This underscores the urgency for sustainable energy solutions. Secondly, emerges as the most promising source of hydrogen production due to its renewable nature. The design of horizontal axis wind turbine with three blades is found to be most effective, balancing stability and energy yield. In addition to that, the critical considerations as location and height are pivotal factors influencing the efficiency of wind turbines. Moreover, blade deterioration poses significant challenges, emphasizing the need for surface composition and bond quality control. This slide explains the steady-state modeling process using HOMER Pro, which is a powerful simulation tool for hybrid energy systems. HOMER Pro is used to size and simulate the hybrid wind energy system, helping identify the most cost-effective and low-risk design by analyzing energy components under various conditions. For this project, I used the location Argentia at Newfoundland. which is located at 47 degree 18.1 minutes north and 53 degree 59.2 minutes west as the simulation site in Homer. This allowed me to access localized wind temperature, solar and water data. Homer pulls this data from NASA's Global Energy Resource Predictions, which ensures accurate and consistent environmental inputs. As shown in the lower right chart, the variable distribution of wind speed at Argentia helps model the variability and availability of wind, which is critical for estimating hydrogen production potential and overall system performance. In our system, we integrate three major components: the wind turbine, electrolyzer, and hydrogen storage tank. The wind turbine serves as our primary renewable energy source, generating power that fluctuates due to variability. To address the intermittent nature of wind energy, we have opted against traditional battery banks, recognizing their lack of alignment with our goal of green, cost-effective hydrogen production. Instead, when the wind speeds are insufficient, we will utilize the grid for a steady power supply to the electrolyzer. Our wind farm configuration consists of 10 numbers of 4 megawatt wind turbines aimed at generating around 32 to 37 kilowatts of power. Any excess power produced by these turbines will be sold to Newfoundland Power, contributing to the local energy grid. Through this integration and utilization of renewable energy sources, our system not only produces clean, green hydrogen but also supports the stability and sustainability of the local energy infrastructure. In our hydrogen production system, the selection of the electrolyzer was meticulously based on its life cycle and the overall efficiency, drawing insights from the references. Each unit of the chosen electrolyzer boasts a capacity of 2 megawatt, contributing to the entire system's rated capacity of 30,000 kilowatt. With this configuration, our system is projected to produce approximately 565,000 kg of hydrogen annually. Furthermore, simulation results conducted in HOMER Pro demonstrate the system's capability to fill the hydrogen tank to capacity within a span of 2 months, validating its efficiency and feasibility for our production goals. This diagram illustrates the complete hydrogen production system powered by wind energy. First, wind turbines generate AC electricity which passes through a three-phase rectifier to convert it into DC. A DC to DC converter then stabilizes this voltage to match the input requirements of the PEM electrolyzer. Water from the natural or treated source is fed into the electrolyzer. Inside it undergoes electrolysis, splitting into hydrogen at the cathode and oxygen at the anode. To make the process more efficient, a recirculation pump is used to reuse water, and a dehumidifier ensures the hydrogen is dry before moving forward. Finally, a backflow prevention valve ensures gas flows safely into the hydrogen storage tank, where it is held for later distribution or use. This slide covers the mathematical modeling of wind turbines, focusing on how power is extracted from the wind. The power output is a function of air density, turbine swept area, wind speed, and the power coefficient. The cubic relation with wind speed means small wind changes lead to large power shifts. The tip speed ratio, which is the ratio of blade tip speed to wind speed, is crucial for wind turbine efficiency. The plot on the right shows how turbine output varies with speed at different wing velocities. We aim to operate near the peak of these curves, where the maximum power coefficient occurs, ensuring optimal energy capture. This slide explains the working principle and modeling of the polymer electrolyte membrane electrolyzer. The system uses a solid polymer membrane which selectively allows hydrogen positive hydrogen ions, that is protons, to pass through, keeping the hydrogen to oxygen generation zones separate. During electrolysis, water is split into oxygen and hydrogen gases. The anode side handles oxidation, where hydrogen molecules lose electrons and release protons. These protons then move across the membrane to the cathode, where they combine with the electrons to form pure hydrogen gas. This model helps us visualize the full electrochemical process, including heat exchange, gas separation, and dehumidification steps. This Simulink model outlines our complete standalone hydrogen production system. The system starts with the permanent magnet generator driven by wind, producing three-phase AC power. This AC is then converted to DC using an AC to DC rectifier and further regulated using a DC to DC converter to match the electrolyzer's voltage requirements. The control unit plays a key role by adjusting the converter's operation based on real-time current, voltage, and speed inputs. All of this ensures that the electrolyzer receives clean, stable power, enabling continuous hydrogen generation even when wind conditions fluctuates. This slide brings together both the physical layout of the hydrogen production system and the Simulink-based control architecture that manages it. Starting with the system diagram, we can see how wind turbines generate AC electricity, which is then passed through a three-phase rectifier and a DC to DC converter. This conversion is necessary to produce a stable DC supply for the PEM electrolyzer, where water is split into hydrogen and oxygen. The hydrogen then flows through a dehumidifier and a backflow prevention unit before being stored safely in the hydrogen tank. Supporting this physical system is a well-structured control unit which shown in the Simulink model. It is divided into two key parts. The outer loop focuses on torque control, receiving reference signals such as desired speed and sends DC voltage to compute a torque request. The inner loop handles current control, regulating the DQ axis current components based on feedback like stator currents, rotor speed, rotor angle, and DC link voltage. These control loops are powered by real-time sensor data, including current, voltage, torque, rotor speed, and rotor position from the wind speed. The goal is to maintain system stability and maximize efficiency, even when wind conditions fluctuate. The final output from this control block feeds into a PWM waveform generator, which sends precisely timed signals to the converter, ensuring smooth and efficient operation of the entire system. This diagram represents the PEM electrolyzer system integrated with wind energy. First, the electrolyzer block requires a steady supply of water, which is maintained by a recirculation pump. This helps keep the electrolyzer operating continuously and efficiently. The power input is managed by a DC to DC converter, which stabilizes the variable DC incoming from the rectifier stage. That rectifier converts the fluctuating AC output from the wind turbine. This configuration ensures the electrolyzer receives the precise voltage it needs to produce hydrogen without interruption, even when the wind conditions vary. This diagram represents the PEM electrolyzer system integrated with wind energy. This Simulink model represents how a real wind turbine works. It begins by simulating wind speed, which drives a mechanical rotation. This mimics the spinning of the turbine blades. The permanent magnet synchronized machine block acts as a generator, converting mechanical motion into electrical power. A rotor sensing block monitors rotational speed and position, which are essential for feedback in control systems. Finally, the system outputs torque, current, and voltage, letting us visualize the energy conversion process just like in a physical wind turbine. In this slide, there are results summarize the performance of our standalone wind to hydrogen system. First, we see that energy consumption increases quickly and plateaus around 42 kilowatt hour per kg of hydrogen. The second plot shows the hydrogen production is over a full day reaching approximately 11 to 12 kilograms, which aligns with our system targets. Next, we see the electrolyzer power demand is closely matched by the wind generator's output, which is critical for maintaining stable operation. Finally, both electrolyzer voltage and generator phase voltage stay stable, proving that our control and conversion stages are working effectively. To summarize, this project successfully implemented a control-driven standalone wind hydrogen system. We achieved a production target of 110 kg of hydrogen per day and at an energy cost of 6 kilowatt hour per kg, which reflects a strong system performance. A major contributor was the reliable and uninterrupted operation of the AC to DC rectifier, ensuring smooth power flow. Additionally, the DC to DC converter with efficiency above 95% helped minimize losses and maintain steady input to the electrolyzer. Our control system played a vital role in meeting production targets by dynamically adjusting to wind variations and regulating output. Looking ahead, there is significant scope of further optimization, especially in refining the control logic to boost system efficiently and sustainably. Thank you for the opportunity to for this presentation and have a wonderful day. Thank you.